Thank you, Jorge. It's my pleasure to be here and see a few very familiar faces again. I'm here to talk about incremental methods for convex optimization. Now, convex optimization is a really hot subject these days. I've been in optimization for many, many years. I've never seen it so hot. And it is hot because a number of other very hot areas, like machine learning and signal processing, what we call big data, very much rely or have relied in the last 15 years on convex optimization. Now, within convex optimization algorithms, incremental methods is also among the very hot type of algorithms. And the reason that they are very hot is that they handle problems that arise very frequently in big data, in machine learning, in signal processing. These are problems that involve the minimization of the sum of a very large number of component functions. And the idea of incremental methods is, instead of operating with all the functions at each iteration, to just pick one and do a little iteration with great economies in overhead and proceed one by one. So anyway, I'm going to explain this as I go. Just a few slides in the way of review and overview. The problem I'm going to be focusing on is minimization of a convex function f of a vector x, n-dimensional vector x. Everything is finite dimensional in this talk. Subject to constraints, x in some constraint set capital X, which is assumed to be closed and convex. It's a classical problem for which there are many algorithms, but I'm focused on two classical algorithms. One is the projection method, gradient projection method, or subgradient projection method in the case where f is non-differentiable. And the typical iteration here is, okay, you are at the current point xk, and now you calculate a gradient, the gradient or a subgradient, if f is non-differentiable, of the cost function at xk. So this unusual notation here, which is convenient for me, stands for any subgradient of f at xk. A subgradient for convex function is sort of a substitute of a gradient, and many convex optimization convex optimization methodology relies on subgradients. Just parenthetically, you can think of this as a gradient if f is differentiable. Now, alpha k is a step size. So what this algorithm does is it starts at the current point, goes in the direction of the negative gradient or subgradient by an amount alpha k, and then projects back on the constraint set x. If there is no projection, the problem is unconstrained. This becomes the classical gradient method, very fundamental. Okay, now there's another classical algorithm which has become very prominent in convex optimization in the last 30 years or so, and this is the so-called proximal algorithm. Here, what we do, instead of calculating a gradient or subgradient of f, we minimize it directly, but we also regularize it. We add a regularization term to f that is centered at this current point xk. Alpha k is a positive parameter, plays the role of a step size, and you minimize, instead of f, you minimize the regularized version, centered at the current point, then you recenter at the next iteration, you reminimize, and so on. So you can see now that this algorithm is more difficult, it requires more overhead than this because it requires full minimization, but the regularization term helps here. However, the nice thing about this algorithm is that it has more solid convergence properties. Despite the fact that it requires more overhead, it's appropriate for problems where this minimization is not overwhelming. And as an example of that, this algorithm converges for just about any choice of step size. Any step size will do. Any sequence will do. Here you have to be very careful about selecting the step size, and there can be a lot of theoretical and practical problems associated with that. The proximal algorithm also has theoretical significance because of its dual version. Okay, I'll get into this a little bit more later. But here what we have is minimization of two convex functions, the sum of two convex functions. And there's a dual version of this minimization in the so-called Fenchel duality framework. And if you dualize this problem, then you get another very important method for constraint optimization, which is the augmented Lagrangian algorithm. This is a general purpose optimization method that you can find. It's very popular. You can find it. It's very easy to implement. And there's software associated with it that people use a lot. So proximal and augmented Lagrangian are dual sides of the same coin, and both of these methods are important. Okay, so now let's talk about problems where incrementalism becomes important. Here we minimize a cost function that consists of a sum of component functions, each of them being convex. And now think of a large number. Think of millions, okay? And this kind of cost functions arise naturally in machine learning problems, for example, statistical problems, regression problems, and the like, where each one of these components corresponds to one piece of data. So if you have 1 million pieces of data, there are 1 million components here. And moreover, when you calculate the full gradient of this function, you have to process all the components, okay? So this is an expensive operation. Now, incremental methods try to get away from that horrendous overhead. So here's how they work, or at least some of the methods I'm going to discuss. Here's how they work. You choose at the kth iteration an index, a component, a single component out of those, and you perform either a subgradient iteration or a proximal iteration using that component only, okay? So here's a gradient iteration, but restricted to that component, and avoiding all the overhead associated with calculating the subgradient of the sum. Similarly here, the proximal iteration uses just one component. And the components have to be selected with equal long-term frequency, but there are a number of ways to do that, by randomization, by cyclic minimization, and so on. So the motivation of this is to avoid processing all the cost components at each iteration, and you hope that you're going to do well with just one component. Now let me bring up another problem, which is important in the context of this talk. It's a classical problem in constraint optimization that involves separability and decomposition. It's a classical resource allocation problem where the optimization vector has components x1, x2, up to xm. Okay, so x is equal to x1 up to xm. It may be a very long vector. The cost function is separable in the sense that it consists of components, each one depending on a single component of x. And so are the constraints. And there are also separable set constraints. And we assume here, for the purpose of this talk, that these are convex. The h are linear in order to get a convex problem. And the capital X's are closed and convex. Now, the nice thing about this problem is that it's very much amenable to duality and decomposition. In particular, if you take this constraint, assign a Lagrange multiplier to it, a lambda to it, and add it to the cost function, then the Lagrangian function becomes decomposable, separable with respect to components. And if you form the dual problem by minimizing the Lagrangian, you get a dual problem like this. Minimize the sum of component dual functions. And each component dual function is obtained by minimization of the Lagrangian associated with the ith component of the cost. So in many applications, this xi is one-dimensional. This minimization is trivial, can be done in closed form, can be done very easily. So calculation of this qi is very simple. Calculation of its gradient also turns out to be simple. And the dual problem has this decomposition property of maximizing the sum of these components subject to no constraints in this particular case. Now here you see the connection between this separable problem and the incremental type of algorithms. The dual cost function consists of components, possibly a very large number. So any algorithm that you can use for incremental minimization can be used also for dual incremental minimization, dual gradient, or dual proximal applied to this decomposable dual problem. Okay, now this decomposition is very classical. It goes to Lagrangian relaxation, which is used very widely in integer programming, dancing-Wolf decomposition, all sorts of interesting methods. This problem has been at the center of large-scale optimization research for the last 50 years at least. In particular, the separable structure is exploited by a method called Lagrangian relaxation, which is a subgradient method for minimizing the dual function, but it's not incremental, but it has a parallel decomposable structure. Now, the proximal algorithm, when dualized, yields the augmented Lagrangian method, but there's a flaw in this. The separable structure that is very evident here and it's exploited by Lagrangian iteration is destroyed in augmented Lagrangian, in the augmented Lagrangian setting, because the quadratic term that's involved in this method couples the terms of the constraint. Now I'm going to get back to this. I'm going to skip for the moment any further explanation, but I'm going to get back later in the talk. Now here's one of the important points of this talk. If you use incremental versions of the Proximal algorithm for this problem, then you can take advantage of the separable structure by passing on to incremental augmented Lagrangian methods, which would involve a restoration of the separability of the augmented Lagrangian cost function. So that's where I'm going. I have primal incremental methods. I have a dual problem that's amenable to decomposition, and I'm going to show that incremental methods are useful not only in the primal setting, but also in this dual setting to produce incremental augmented Lagrangian algorithms that exploit the separable structure. Okay, I'll talk about some other stuff at the end, but that's the broad outline of my talk. So there are a number of references for this. Joint and individual works with two of my students, Angelia Nedic and Mengdi Wang. Angelia is a professor at the University of Illinois in Champaign-Urbana. Mengdi Wang is at Princeton University. And our works go back 15, 20 years, and they focus on convergence, rate of convergence, component formation, component selection, all these mechanics of these methods. And there are a number of references, which you can find on the internet. And as general references, there's a convex optimization algorithms book that I published last year that has a lot of this material, although not all of it. And I'm publishing a third edition of my nonlinear programming book. That's going to be out in a couple of months or so. And this also contains a fair amount of this material. Okay. So this is in the way of orientation. And now I'm going to get a little bit more into the mechanics. But feel free to interrupt me if you have questions, and I can explain. I'll first talk about incremental algorithms in the primal setting. Then another type of incremental algorithm that I didn't discuss so far called aggregated. And this is really very hot. People are very much looking at ideas involved in this algorithm. Then I'm going to look at incrementalism in a dual setting involving augmented Lagrangians. Then I'm going to discuss incremental treatment of constraints. To the extent I have time, I'm going to get into that, and also the convergence analysis. Okay. So let's talk about incremental subgradient methods. And here is the problem again. Minimization of the sum of components subject to a convex constraint set. It's a long history to this problem. There's an important paper from 1960 by Woodrow Hoff. It's very, very well known in signal processing. And I think it was the first, at least deterministic type of incremental method, and it was applied to linear least squares and without projection, without any constraint. Then you can find incremental methods in the Soviet literature from the 60s, particularly in the context of stochastic subgradient methods. Then there is a parallel, to some extent, literature of stochastic approximation that goes back to the 60s, and even before that. Then there's a big explosion of interest in neural networks in the 70s, which use for training incremental methods. The so-called backpropagation method for neural network training is an incremental gradient method. Of course, the problem there is non-convex, but nonetheless, the ideas are very similar. Neural networks were very hot in the 70s. Then the interest subsided, sort of reached some kind of a steady state. But now there's an extreme interest in them again through the focus on deep neural networks and what they can do in a number of application settings. Okay, so here's the basic incremental subgradient method. I explained it. You pick one component out of the many and do a little subgradient step using that. And the step size can be chosen a number of different ways. The standard way, you might say, is this diminishing step size. Okay, the alpha k's are diminishing to 0. However, they diminish at a rate that's not very fast. It has to be just right, okay? And you have this is a standard rule. Another possibility is to use a constant step size, and we're going to see that convergence under a constant step size is very problematic. And then there are other methods dynamically chosen and so on. There's a large variety of different ways. And also, let me mention the selection of the index. It's possible to choose the indices cyclically. You start with component 1, go to 2, go to m, and then go back to 1, and cyclically repeat. Another possibility is to choose the index to operate on randomly with equal probability. And people very frequently in practice use a combination of these two. Reshuffling. This method is cyclic, but at the beginning of each cycle, you reshuffle randomly the order of the indices. And this tends to combine the best, well, tends to work very well in practice, and it's easy to implement, and people use it a lot. Okay, so that's the basic incremental subgradient method. And why should this method work? It looks like quite an unusual and crazy method, because you're not using the correct gradient. You're using some sample of a gradient that has a lot of error. So why should it work? And why should it work well? And here's my explanation for it. Let's look at an example, a one-dimensional example. This is a least squares problem, minimizing the sum of these squared terms. X is one-dimensional. Ci and Bi are given. So each one of these terms is a quadratic. X goes this way. Each one of these is a quadratic. And you're trying to minimize the sum of these quadratics. And of course, the minimum of the sum is somewhere over here, somewhere in this region between the minimum of the minima and the maximum of the minima of the component. Okay. So now, how would the incremental method work? The incremental gradient method, suppose that it starts at some point far to the right. Then it will pick a component, one of these quadratics, and no matter which component it picks, it's going to go in the right direction. It's going to move to the left towards the direction, towards the location of the minimum. Similarly, if you start far out to the left, you're going to be going in the correct direction, regardless of the component that you pick. You would be doing exactly the same thing that the gradient method would do, but at a much, much more overhead. Okay? The gradient method would also go in this direction. However, it will calculate the sum of the gradients of all of these, which is a much more expensive operation. So, far out, in this far out region, to the right or to the left, the incremental method does things similar to the gradient method, but much, much cheaper, like day and night. We're talking about many orders of magnitude of improvement in terms of computational efficiency, as long as you are in this far-out region. On the other hand, once you get into this region of the minima of the components, which I call the region of confusion, the method gets confused. Why does it get confused? Well, if it's over here, and it really wants to go here, but by accident, it chooses this component, it's going to move in the wrong direction. In other words, here, using wrong information matters and confuses you, and the method, at least with a constant step size, would be oscillating right here. Let me also mention, I see here Trasivoulos Papas, who was my former student, a master's student from MIT. I understood this phenomenon together with Trasivoulos when he was doing his master's thesis back in the early 80s, I guess it was. Okay. So we have this confusion. Even if you start at the minimum, you're going to get confused. So what do you do in this case? Well, the only way you can make the method converge is to reduce the step size. So these confused steps become smaller. They average each other. And on the average, you get a good trend, a good direction to move. And then you can prove convergence. That's why you need diminishing step size. This method will not work with a constant step size, but it will work with a diminishing step size. And because it will use a diminishing step size, it will also converge slowly, very slowly, sublinearly, whereas the gradient method, once it gets here, asymptotically, it's much more efficient because, for this problem at least, it converges linearly. So that's the broad outline of what's happening. Fast convergence, very fast convergence, great efficiency when you are in the far-out region, and then when you get in the region of confusion, things become garbled, and you can't expect fast progress. On the other hand, if you can tolerate some error in the accuracy of your solution, this method is just great in terms of how fast it can get to the proper area. Okay, of course, this is a one-dimensional example, but conceptually, the idea generalized to higher dimensions, although it's difficult to quantify this analytically. Even though the analysis does not show this phenomena, I think this is what's really going on here, and it's been confirmed by a lot of experiment. If you believe this picture also here, you understand why it's important to adapt the step size so that when you are in this region here, you use a smaller step size than when you're far out here. There are methods that sort of detect when you are in the region of confusion and then automatically try to reduce the step size. And people have tried a lot of different schemes along that line. Another thing to understand that follows from this figure is that by shaping this region of confusion and making it smaller, you may enhance convergence. How do you shape this region of confusion? There's a certain technique called mini-batching, where you lump together batches of these square terms, and that tends to shrink the region of confusion. So the undesirable phenomena happen later in the computation. Epochs.
If I have only seen the data once, then the stochastic gradient method is very efficient. And once I start revisiting the data, it becomes less efficient. So there are two different explanations.
Okay. Later I'm going to discuss this aggregated incremental method, which becomes effective precisely after you've seen the data once. And then you can reuse what you have seen to make this idea more efficient, except that in the aggregated method, there's no region of confusion. Once you've seen the data, then you're not confused anymore. You're trying to minimize the error associated with the gradient. Okay, so Okay, so this holds for incremental gradient. Now, incremental proximal, remember, you select an index and you do this proximal minimization with a regularization term at the current point. And this is more economical, of course, because you use only one component of the cost function. This method is very similar to the incremental subgradient method. The step sizes are chosen in a similar way. Index selection schemes are chosen in a similar way. If you think about it, this far out and confusion regions can also be viewed in the context of this algorithm. And here's another insight here. It is possible to write this equivalently, this incremental proximal minimization as an incremental gradient minimization, incremental gradient iteration, but with a subgradient evaluated not at the current point xk, but rather at the new point. So this becomes an implicit iteration, which is difficult to implement. However, the fact that this algorithm can be written like so tells you something about the close connection between incremental subgradient and incremental proximal. They're really almost the same. If the step size is small and this iterate is close to xk, then they're almost the same. Okay, so the point I'm making here is that incremental gradient and incremental proximal are very similar in terms of their behavior and some of their analysis. Why would you want to use this? Well, it's slightly more stable. It sort of tends to inherit the stability of proximal iterations. So if you can use it, you'd prefer it. But the difficulty, of course, is that it may be harder to implement because you're minimizing a full component function. But here's an idea that comes naturally. You have this sum of components to minimize. Take a component. If it's easier to do for that component the proximal iteration, you prefer that. If that's difficult, then you use a gradient iteration. So it gives you the option to do one or the other, and the convergence properties are exactly the same as for the case where you use only one algorithm and you don't mix them together. So that's the idea. Use the proximal when it's easy to implement. Use the subgradient otherwise. It's a very flexible implementation. And notice that because of these ideas with far out and regional confusion I mentioned, you still require a diminishing step size for convergence, no matter how you implement this method. Okay, there are these convergence analyses associated with this. You need diminishing step size. You have convergence to a neighborhood of the optimum. You have the method oscillating with a amplitude of oscillation that's proportional to the step size if you use a constant step size. And a nice result is the following. If you use index selection by randomization, then you have a better complexity. A better complexity result is obtained with randomized index selection. That's a non-trivial result to prove, and the most exciting out of the ones that I mentioned here. The thing is that if you use a cyclic index selection, you might fall onto a bad index, a worst-case index, which will destroy the complexity estimates and make them much worse. In practice, this has also been seen, but there are problems where you know a good deterministic order, which is preferable to a randomized order. All of this comes out of the analysis, and I'm not going to go into that any further. You may look at the corresponding papers. Okay, so I talked about incremental methods. Now I'm going to talk about aggregated incremental methods, which offer similar advantages, but they have a different explanation as to why they work. Okay, the incremental methods are all the rage nowadays in optimization algorithms. People do a lot of work in this area because they have discovered that under some conditions they offer better theoretical convergence rate and practical convergence rate. Here, instead of using a single component subgradient, we use the subgradients of all the components. However, we calculate a new the subgradient of a new component only once, only one component per iteration. And you reuse the previous subgradients to form an estimate of the full gradient. Okay, the thing to notice here, and I'm sorry about the notation, it's getting a little bit hairy, the index of the x at which you calculate this subgradient is Li, which is something that may be smaller than k. In other words, this is a delayed index. This subgradient is calculated at previous iterations. You are at iteration k, you pick a component, calculate subgradient, and then tack on other subgradients that you've calculated from previous iterations and form an estimate of the full gradient. So there are delays here, and that's the method. So that's the key idea. Only one component subgradient may be computed per iteration. And this idea is actually very obvious. It appears in one of my papers with Angelia Nedic and Vivek Borkar. And there we were looking at parallel computation. We're looking at non-differentiable cost functions, diminishing step size. The key work, the important work in this context came later by these three people in 2008, where they assumed a differentiable, strongly convex. Actually, they assumed quadratic components in their proof, no constraints, and showed that this method converges with a constant step size, not a diminishing step size, and has a linear convergence rate, which is pretty much similar to the one that you have for the non-incremental method. So this is a big thing. For a fraction of the cost, you get the same properties that you have for the gradient method. And people focused on that, and they improved the convergence analysis of Blatt-Heer and Gauchman. In terms of how this method works, it's not really an incremental method in the sense of having a region of confusion. This is really a gradient method with an error in the calculation of the gradient. And that error is proportional to the step size. And it turns out, it's not at all obvious, that with this error, still you get the linear convergence under, certain assumptions, of course. So it's a fundamentally different convergence mechanism. It relies on differentiability and aims at cost function descent. There's no region of confusion. And there are some drawbacks. And coming back to your question, this method becomes effective after you have gone through the data, you have gone through all the components once in order to build an approximation to the gradient. And of course, the number of components may be millions. And if the number of components is very large, you hope to converge for practical purposes before exhausting all the components. Okay? That's the way practice works. If you have a very large data set, you only go through the data set once, or even halfway, or even a small fraction, and you're there. Okay? So so for many problems, this idea would not find much application. But in any case, there are a lot of interesting work, and in the general form that I'm giving the result here, there's a nice paper by with Balaban, Asmanus Daglar, and Parillo from MIT, who are my colleagues, and they have a particularly elegant proof of convergence. If you look at some of the earlier proofs, they're just horrendous, just completely undecipherable. You know, like we were talking about proofs that 20 pages dense with epsilons and deltas. So, okay, so I don't think you can read a proof. Like, nobody knows if these proofs are correct, okay? Because nobody has ever read them. But anyway, this is just an indication that these convergence proofs are non-trivial, and these guys have a particularly nice proof that's only 2.5 pages long. Okay, now just as there is an incremental version of the gradient method, an aggregated version of the incremental gradient method, there's an aggregated version of the proximal method. And this works as follows. You pick one component at iteration k, you select this index, you pick this component, and you approximate the other components by linearization using the gradients that you have computed earlier. And you do this proximal minimization, and these are delayed subgradients, and you assume that the delays are bounded. There's an equivalent way to write this iteration, because this is linear in x, and this is quadratic, and you can complete the square here and write the iteration like so, where given xk, you recenter the quadratic form by moving it in the direction of the subgradients, and then you plug it in here in place of xk. And this is equivalent to this method here. From point of view, practical point of view, the two approaches are not different. And you can prove the same result as the one of Balaban, Ozdaklar, and Parillo for this method. Linear convergence rate with a constant step size, provided the FIs are differentiable and strongly convex. And again, you have the option of combining the two methods and so on. Okay. So we have incremental methods. We have the pure version and the aggregated version. And now I'm going to switch gear and go into separable convex optimization and see how we can get corresponding incremental augmented Lagrangian methods, both pure and aggregated. So we go into augmented Lagrangians now. And here's the problem. Minimize a separable cost function subject to separable constraints. Convexity assumed throughout. I'm just repeating what I said before. The dual problem decomposes into and can be written as minimizing the sum of dual components, and becomes suitable for application of the incremental ideas. The incremental subgradient method exploits the separable structure. The proximal does not, because we're going to see that this augmented Lagrangian is not separable, and I'm going to focus on how we can get around this problem by using incremental ideas. Okay. So here's my dual problem. It involves the sum of these dual functions. You are at a certain point lambda k. You center your regularization term at this lambda k, and you maximize. Here we have maximization because the dual problem is a maximizing problem. So we switch to maximization. Okay. Now, viewing this as the difference of a concave and a convex function, and using Fenchel duality, introducing primal variables x, it turns out, and I can't go into the details, it's sort of a classical transformation, that there's an algorithm based on this augmented Lagrangian function. This is the ordinary Lagrangian function that involves, okay, lambda multiplying the constraints. And there's a penalty term also, with alpha being the penalty parameter. That's called augmented Lagrangian by this term here. Notice that whereas the Lagrangian is separable, the augmented Lagrangian is not separable because in the quadratic, the components are coupled. Okay, so with this definition of the classical augmented Lagrangian method minimizes the augmented Lagrangian for a given lambda k, and then updates lambda k according to this iteration. Okay, so if you have found xk plus 1 from here, you plug it in here, and you move in the direction of the constraint, which turns out to be a gradient. The gradient of the dual function turns out to be this. This is a gradient iteration. Now, what we're going to do is use an incremental gradient iteration where the summation is going to go away. Theoretically, there's not much that's involved here. Proximal algorithms and augmented Lagrangian algorithms are entirely equivalent. They're dual sides of the same coin. So anything you can apply on the primal side, you can also apply on the dual side. What we're going to do is apply on the dual side an incremental proximal idea. So here is the incremental proximal algorithm for the dual problem. Pick an index, do a proximal minimization with the corresponding dual function component. Again, you have the property of maximizing the sum of a concave function, a convex function, and you can dualize this using differential duality. And once you do that, here's the algorithm that you get. You pick a single component, you minimize the Lagrangian of that function, of corresponding to that component, plus only a part of the constraint function. Of course, this is all separable. You do this little minimization for a single component and keep all the other components constant. And then you update the lambda according to this. So this algorithm updates the lambdas much more frequently. Uses only one component and updates the lambdas. Of course, it requires also a much smaller step size, and in fact, a diminishing step size in order to have convergence. Okay, so this is the incremental method, and now let's look at the aggregated method. The aggregated method, again, picks a single dual function component, recenters the proximal term by moving in the direction of the gradients of previous components, and then does again this minimization. Again, you have the differential structure, maximization of a concave and a convex function, and after you use that, here's what you get. This is an incremental aggregated augmented Lagrangian method. Pick an index, minimize a component augmented Lagrangian corresponding to that index. This is the optimization component, and you recenter the quadratic, you recenter the penalty, but at values of previous components. So this is a one-dimensional minimization, essentially, or small-dimensional minimization. And the separability issue has been overcome. The other components are kept unchanged, and now the update of the multipliers is done by an incremental aggregated gradient method, where this is the gradient of the current component, and these are the gradients of the previous components. So everything works great here, except for one fact, that the step size has to be chosen carefully and diminishing. In augmented Lagrangian methods, normally you'd like to take the step size to increase, not decrease. So whether this is a good idea or not depends on the problem. If incrementalism gives you a lot of benefit, then perhaps this is a good idea. But the jury is still out on whether and for what problems this algorithm is good. Have I exceeded my time? 15 minutes. I have 15 minutes? Yeah. Whoa. I can go into new stuff. Okay, thank you. Okay. Now let me mention another method that's also at the center of of convex optimization research now. It's the alternating direction methods of multipliers, ADMM. The interest on those is just phenomenal. Like, 2,000 citations in the last couple of years or something. They're old methods. They go back to the 80s. And they can be used for decoupling of components in various cost functions and constraints. I'm not going to discuss the broad method, just its application to the separable problem. It turns out that the ADMM gives you another way, and a very solid way, to decouple the components in separable constraint optimization problems. Here's how it looks. In the context, it involves augmented Lagrangians, and remember that we're minimizing the sum of the f's subject to the sum of the h's being 0. At the current iteration, we have a vector xk, and we look at each component and do this minimization that involves only that component. Okay? Only xi is involved here. All these other terms here, all these other components come in, but but they don't enter this minimization. They come from xk. And then we update lambda k according to this. If you look at this iteration and the other one that I had in the previous slide, the incremental, they are pretty similar. But here at each iteration, you don't minimize with respect to a single component, but with respect to all components, but separately from each other. It's a very clean algorithm. It's a very old algorithm. This is the reference there. It's to my book with John Sickless from 1989. I have counted about 15 papers or so dealing with this problem and giving algorithms that are related to this and explaining why they don't work and why you need additional assumptions. But in fact, you don't need additional assumptions. All you need is to have the right algorithm to make the right transcription. It was there in the literature, but in this field, everything that's older than 10 years, it's as if it never happened, okay? So anyway, let's compare this algorithm with the incremental one and see why they have fairly similar operations. Okay, this is the incremental. The main difference here is that you update a single component for iteration before you go into the multipliers. Here you update all the components in parallel, if you wish, and then you update the multipliers. The ADMM has guaranteed convergence for any constant alpha. Okay? It's a great thing about the ADMM. Any step size, there are no problems with step size. And under weaker conditions, you don't need dual differentiability, you don't need strong convexity, and all this other stuff. Just convexity is sufficient for convergence here. On the other hand, the incremental aggregated method has step size restrictions and pretty serious ones. On the other hand, there's a lot more overhead in each iteration of the ADMM because all components are updated, and the overhead is m times larger, and the number of multiplier updates are much less frequent. So how all this shakes up in particular problems is not very clear, but it's an interesting subject to look into. Okay. The last topic has to do with incremental treatment of constraints. Here I'm generalizing the problem. Minimize the sum of components subject to a constraint that is itself the intersection on many simple constraints. So you can view this constraint as being the sum of the indicator functions of simpler constraints. Each one of these components is closed and convex. And here is an incremental constraint projection algorithm. Here we treat incrementally not only the components of the cost function, but also the components of the constraint. So at the kth iteration, we pick one component from here, and we pick one component from here, an index ik and lk, and we perform a subgradient iteration or a proximal iteration using only these two components. Notice that the projection is done on the simple component set. And similarly here, the minimization is done only on the component set. So if this is a complicated polyhedron, the intersection of half spaces, you can choose as components half spaces, which makes this minimization much simpler, and this projection trivial. That's the big thing about this incremental treatment of constraints. It simplifies the minimization a lot. Otherwise, these iterations are similar as before. This component subgradient, and this is a proximal iteration involving only a single cost function component. Now, this type of method is relatively recent. I think the first time I saw a method like this was in a paper by Angelia Nedich from 2011. However, special cases of this algorithm go way back into the 60s. And the special case that has been looked at a lot is the alternating projection method for finding a point in the intersection of convex sets, a large number of convex sets. This method is obtained when the cost function is identically zero. Zero cost function, just a feasibility problem of finding a point in these constraint sets, a common point in all of these components. So you have this constraint set, you have this other constraint set, and now this method involves, this term goes away, involves projections. So you project on one component, then you project on another component. Alternately, you go around the components, and you obtain this classical alternating projection method. These methods go way back. I think there was a method like that proposed by von Neumann back in around 1950 or so. But they were looked at intensively in the 60s in the Soviet Union, and then later in the United States. This has been quite a bit of attention. The name of Bauschke is associated with these methods. He wrote his thesis on this subject. There's a book by Bauschke and Convex, which deals a lot with these methods. Okay, so now we want to generalize these alternating projection methods, where we have, in addition, a cost function. So we want not only to find a feasible point, but we want to find an optimal feasible point. So there are two objectives here. One is an optimality objective, the other is a feasibility objective, and this is reflected in the structure of these algorithms. This part tries to achieve optimality. This part in the projection tries to achieve feasibility. So let's see how the methods would work. Okay, one thing that I want to point out that is diminishing step size is important. And what we want to achieve is progress towards feasibility through the projection and progress towards optimality through the subgradient and proximal iteration. And here's the picture. Here's how the convergence issues shake up. Okay, let's focus on this figure here. The green area is the constraint set, is the feasible region. So you have two constraints. One is this, and the other one is that, and the green area is the intersection. And you have a cost function that has contours, as you see here. So the optimal point is this x star. That's where you want to get. But you want to get there from infeasible points. And the gradient projection method goes entirely through feasible points, starts at the current point xk, takes a move along the negative gradient of the cost, and then projects back to this point xk plus 1. A move that may take you infeasible and then project back. This is the gradient projection method. The alternating projection method aims at feasibility. This method aims at optimality. This method aims at feasibility. It works as follows. It is somewhere outside the green area that you want to go, projects on one constraint, then on another constraint, and so on, cyclically, and you converge to this point over here. So now we want to marry these two in this incremental projection type of method. But if you try the simple ideas, you see that you may get stuck. Okay, here's what happens when you marry this method and that method. You are at this point xk, you take a gradient step, okay? You move in the direction of the gradient, you end up to this point, and then you project on one of the constraints. At this point, you take another gradient step, and then you project, and you end up exactly where you started. In other words, if you're not careful with the step size, you can get stuck here because the two methods may be working at cross purposes. You have to make one of the two methods subsidiary to the other through a 2-time scale convergence process. Like here, we make the blue method slower than the red method and take smaller gradient steps and full projection steps. Then you end up here, you started here, you end up closer. And then with smaller and smaller gradient steps, a diminishing step size for the gradient steps, you manage to get this red method, the projection method, faster And the blue method sees essentially the problem as being feasible point, because the other method converges much faster. So progress to feasibility should be much faster, should be faster than the progress to optimality, and the gradient step sizes should be less than the feasibility step size of 1. And that's what comes into the convergence proof. Okay, now I'm going to rush a little bit. Various assumptions on sampling for the constrained index. One possibility is to do nearly independent sampling. You pick these constraint sets at random and independently. Cyclic sampling involves either deterministically picking the constraints or reshuffling them at every cycle. It's another scheme, most distant constraint sampling. You project on the constraint that's most far away from where you currently are. Okay, that may involve some overhead, but it turns out that it has better performance, and it can be approximated in some heuristic way. There are also other schemes, Markov sampling according to an ergodic Markov chain, how you pick the constraint index. All of these sampling schemes are possible, and they have their place in various contexts. Okay, now how do you sample for the components? One is random independent uniform sampling. Sample the cost components with equal probability, 1 over n, m, independently of other choices. Cyclic sampling, Markov sampling according to the state of a Markov chain. There are all these possibilities. And the theorem here is that all of these schemes, if you marry any of these constrained sampling schemes and any of these cost component schemes, and you assume, okay, Lipschitz continuity of the cost function as well as convexity, Lipschitz continuity, right, linear regularity of the constraint set. This is a standard assumption in feasibility methods, and I'm not going to go into that. And it's necessary in order for the alternating projection method to converge fast. Non-emptiness of the optimal solution set, then the result is that the sequence xk generated converges to some optimal solution with probability 1 under any combination of the previous sampling schemes. So it's one theorem fits all, and the reason that it fits all is that the convergence proof fits all. And the idea of the convergence proof is that there are two convergence processes taking place. Progress towards feasibility, which is geometric thanks to this linear regularity assumption. So the feasibility process goes fast, and progress towards optimality, which is slower because of the diminishing step size, alpha k. And then we use a 2-time scale convergence analysis idea in the context of a super martingale convergence theorem that involves these two measures of convergence. Usually, incremental methods are analyzed by super martingale convergence type of analysis, but here that would not be sufficient because of the 2-time scales. Anyway, both of these convergence measures, the distance to the constraint set, the expected distance of xk, the current iterate to the constraint set, is involved in this theorem. And also the distance to the optimal solution set is involved in this theorem. And these two measures coupled together in an iterative super martingale equation, two equations, which give you the result that you want, which is this here. Okay, I just wanted to leave you with a theorem. There's a lot more in the way of theorems, but I can't go into that. I try to focus on explaining the main ideas. And I'm finished. There's interesting convergence behavior, both for incremental pure and incremental aggregated. It's possible to have proximal methods as well as incremental gradient, subgradient. You can combine them seamlessly for better reliability and convenience. There's a connection with augmented Lagrangian methods because proximal methods are dual versions of augmented Lagrangian methods. And it turns out that the incremental versions can take advantage of constraint problem separability. Finally, constraint projection adds an additional layer of flexibility for problems that have difficult constraint sets and you would like to project on only a component. And finally, something that I did not mention, you can implement methods like that in a parallel computer setting with asynchronous computation. The asynchrony coming from these delays that I mentioned earlier. These delays may be unpredictable. As long as they are bounded, then you still have some of this convergence analysis holding through. And in fact, my entry point to these incremental methods was precisely the distributed asynchronous part. But there's also quite a bit of work on distributed asynchronous computation these days in convex optimization, and these incremental methods couple into that. So I thank you very much.
Well, let's do the following. Since we have tomorrow scheduled at 12:30 a roundtable with Dimitri Bersekas. This was a very brilliant technical talk about optimization. Tomorrow we will have a wide-ranging discussion about many of the areas that you worked on, just verbally. We did it one time for dinner, I think a couple of years ago, and I thought that would be interesting. So let's defer the questions.